Hello everyone, and welcome to the third episode in this series where I'm building a portable synthesizer. So in the first episode we created the keyboard interface, which allowed us to take inputs from a keyboard, and in the second episode we created the audio module which could play audio. In this episode we're going to be joining the two halves together. Okay, so what we have here is the front-end module we made in the first episode and the back-end module we made in the second episode. And essentially with breadboards you can always just clip them together like Lego bricks almost. Next, what we need to do is connect the ground lines. So you can see here we've got our power rails, and at the moment they're not connected, but we can add this little grey wire over here to connect those. Next we need to connect the ground of this one to the ground line. This one's already connected because we were using that to power this, but this one was by itself until now. Now that we're working with two microcontrollers, we're going to have an additional problem, which is that previously we were able to power them with the USB cable, but since I only have one USB cable, I'll only be able to power one of them at a time, and so we need to have an external power supply which can power the other one. So what I have here is just a standard power supply. If you look closely, you can see that it's a 5 volt 1 amp power supply. And what that means is that on this end there's two terminals, and the power supply is going to try and maintain 5 volts at all times. However, at most the power supply is allowed to supply 1 amp of current. So just a quick word about power adapters. So on a power adapter you're going to see this label here which says the output is 5 volts and 1 amp in my case. And what that means is that the terminal between the two prongs is always going to be at 5 volts, and that's maintained by the power supply. However, the current needs to change according to the resistance, and that's defined by the equation V equals IR. So as the resistance goes down, the power adapter needs to supply more current in order to maintain the 5 volts between the two pins. So at 5 volts and 1 amp, if you do the maths, it means that the minimum resistance our circuit can have is 5 ohms. Once the circuit goes down below 5 ohms, what that means is that the power supply is going to need to supply more than 1 amp, and that's going to break a fuse, which is probably going to burn something out. So one way to think about this is that we have an amps budget. In this case we have an amps budget of 1 amp, and each component is going to draw a certain amount of amps, and if the total amount of amps goes above 1 amp, we have a problem. We need to get a better power supply basically. So the TNC draws around 100 milliamps, and we have two of them, so that's 200 milliamps. The DAC draws around 3.5 milliamps, which is basically nothing. The screen draws around 150 milliamps, and the keyboard draws another 150 milliamps. So in total, we're drawing around 500 milliamps, which is half of our total amps budget. So we're well under budget, and everything looks good. So I'm going to plug this guy in here. We're going to plug the ground wire into the ground rail here, and then we're going to plug the live wire into a separate point here. The reason I don't want to plug it directly into the rail is because I'm going to use these switches to be able to turn it on and off. But if I plugged it directly into the rail, that would mean that it would always be on. So these switches are 3-prong switches. Essentially the way these work is that the middle prong is either going to be connected to this one or to this one. So when the switch is over to this side, these two are connected and this one's connected to nothing. And if we flip the switch, these two are connected and this one is connected to nothing. So I'm going to have two switches here, one to control the lower microcontroller and one to control the upper microcontroller. So now I'm going to connect this live wire to the middle prong of these switches. Now from here we could directly plug the switch into the 5 volt pin for each microcontroller. But what I want to do is add these LED indicator lights, which will tell me when the switches are flipped. So in order to do that, I'm just going to add some wires here. These wires are just to give me a bit more space, so I have enough space to plug in these LEDs. So here I can plug in the LED, and this side's positive, and then the next side will be negative, and you can tell that by the length of each leg. So the long leg is the positive leg, and the short leg is the negative leg. Lastly, we need to connect the negative leg to ground, but instead of directly connecting it, we need to make sure we use resistors. And this is because, like I explained earlier, we need to make sure that the total resistance of our circuit is greater than 5 ohms. In this case, I'm going to be using 5,000 ohm resistors because I really want to make sure we limit the current going through these LEDs. What that means is that 1 milliamp will be going through each LED, which is a very small amount of current, but will be enough to power them so I can tell when these things are on. At this point, we can plug in our circuit and make sure that the indicator lights are working, which means that we've wired everything up correctly. It's also wise when using these power supplies to make sure that the 5 volts that's on the package is actually what's being outputted. So I have here a voltmeter and I can set it to be measuring volts, and then we're going to measure the voltage between the two prongs to see if it's actually 5 volts or if it's something different. So indeed it looks like the package wasn't lying and this is in fact 5 volts exactly. So that means that we're good to go, and we can plug this into our microcontrollers so that we can be able to turn on our microcontrollers from the external power supply instead of having to rely on the USB. So now our microcontrollers are plugged in through these switches into their 5 volt power inputs. So let's quickly talk about UART. UART stands for Universal Asynchronous Receive and Transmit. And you can kind of think about it like another one of those telegraph monkeys that I talked about in the previous episode. USART and UART sound very similar. In fact, in the previous episodes I did refer to USART. In our case we'll be using UART, and the difference is that with UART you have no clock signal, so both sides need to agree on a certain frequency, but there's no actual synchronization going on there. So on Teensy we actually have 8 different UARTs to choose from. They're labeled here on this pin diagram with the RX and TX pins. So for example here you've got RX and TX2, RX, TX1, and so on. So you've got 8 of them if you look at the pins there. So this is kind of what we're going to imagine here. We've got one end which is going to be the transmitter, and it's going to be sending signals through the wire, which are binary signals. And then on the other side we've got the receiver, which is listening to those signals. And then on both sides we have the CPU, who aren't disturbed by this. They're going to continue on with their work while these two sort of worker monkeys do their thing. So just a quick note before we continue about notation. So 1 byte is 8 binary digits, and another way of writing that is as 2 hexadecimal digits. So in this case this byte here can be written as C5 in hexadecimal. And in order to differentiate hexadecimal from decimal, we use the prefix 0x. So in our example, this byte right here can be written as 0xC5. So let's imagine for a moment that we're that receiver monkey who's listening to all the bytes that's coming from the transmitter. And you've got to imagine that maybe it's a little bit confusing because what he's just seeing is these bytes coming in. And it's really hard to tell what these mean. And in particular, it's impossible to know exactly when the message is supposed to have started. Is this the middle of a message? What does any of this mean? In order to work this out, we can define a protocol. And that's essentially just a set of rules that both sides agree on so that they can interpret the bytes. So in my case, I've devised a pretty simple protocol. Every message is going to start with this AB byte. Then we're going to have another byte for the header. And then we're going to have some number of bytes, which is the contents of our message. To show what I mean, I'm going to show you the 5 different messages which I've defined as part of my special protocol. So the first message is the note press message. It's going to start with AB, like all the messages do. Then it has the header, which is 81, and that defines the message type, which the receiver is going to know now that it's a note press message. And then finally we have the data here, which is just going to be a single byte, which is the note number that we're pressing. Similarly, we have note release and note off. The difference between these two is that note release is going to play the release envelope, but the note off will just turn the note off immediately. Then we have set parameter, which is slightly different from the others because we have 84 as the header, and then we have 1 byte as a parameter, and then we have another 4 bytes which define a 32-bit float value. And the receiver is going to know that this message is longer than the others because of this header. So the length of the message is purely determined by the header. Lastly, we have the notify awake message, which the front end is going to send to the back end just to tell it that it has turned on and it's available to transmit. So let's look at an example here. This is kind of a string of bytes that the receiver might be looking at. So it's going to start from here. So first it receives these 2 bytes, but because it hasn't received the message start byte, which is AB, it'll just ignore those, and it will keep ignoring bytes until it receives AB, which it does here. From there, it knows that the next byte is going to be the header. 8.1 corresponds to note press, so then it knows that the next byte after that is going to be the note number. So overall, it will pass this message as plate note 0x24, which remember that's hexadecimal, so in decimal that's note number 36, which on a keyboard would be A3. And then similarly, we have a message here for setting a parameter, so that's 8.4. Remember, 8.4 is set parameter. It's going to set parameter number 3, and then these 4 bytes represent the floating point number, which when you decode that, you get 3.42. So in all, that means that you've got to set parameter number 3 to 3.42. And you can kind of see how this would go on, and it would be able to decode any number of messages. So how can this go wrong? So let's imagine that the receiver and the transmitter have fallen out of sync. Usually that's okay because the receiver is just going to ignore any bytes until it receives the next message start header. But it is possible for the data part of a message to also contain the byte AB. And what that means is that eventually the receiver could erroneously think a message has started halfway through another message. And in that case, it would just sort of read random values, and it might do something a little bit strange. So what are the conditions for this bad behavior to happen? Well, first of all, the two must have fallen out of sync. So that means that they must have missed a byte somewhere. And then the AB byte has to just happen to appear as part of the data package of another message. And then finally, the byte after that has to be a valid header byte, which there's only 5 of. So all in all, this desync risk is quite low, and I'm willing to risk it, and maybe occasionally we get a weird glitch, but overall I think it's pretty safe. Lastly, we need to do what we set out to do with the UART, which is to actually make sure that these things can communicate with each other. So now they can be powered independently, but in order to get them to communicate, we need to use the transmit pin on the lower microcontroller, and we need to plug that into one of the receiver pins on the upper microcontroller. So here I'm going to use pin 14 and pin 25, and I chose those pins because they're quite close to each other when we lay out the circuit like this. But you could have chosen any pins you wanted. And there we go, this is our completed circuit. So now we'll be able to plug in the USB on one of the microcontrollers and then turn on the other separately. And this is going to be needed once we have this one communicating with this one. So on the other side of my desk now, I have the full setup here. So this is the keyboard, and here's the circuit we just built. So now I can turn both of these on. And oh, looks like the LED light's a bit dodgy there, but trust me, it's on because you can tell the keyboard is now responding, which means that everything is working as we'd hoped. Now that we have the thing set up, we can also plug in the USB, and make sure when you plug in the USB that you turn off the external power supply for that side. What you're going to notice though is that the LED is still going to turn on even if this switch is off, and that's because due to a strange quirk inside of the Teensy's design, the 5-volt input pin also emits 5 volts when the USB is plugged in. But don't worry about that, it just shows you that the thing is on. So now we can see that the keyboard's turned back on. That's because it's getting power from the USB instead of from the power supply. And if we wanted to then work on the other microcontroller, what we have to do is just unplug that, turn that one off, plug in the other one, and turn this one on. So there we go, that's our setup for working on the microcontroller. Now that we have the power supply, we can work on one with the USB and power the other with the external power supply. So in order to implement the UART in the code side, what I've done here is created 2 files, tx backend and tx backend C++. And these files are on the front end and they're transmitting to the backend. So here we use the Arduino serial object, and in this case we're using serial object 3. So here we define a number of methods, and each of these methods corresponds to one of the possible messages we can send through our protocol. Inside each of these methods, we then first begin the message with a message begin, which is AB, as we defined earlier. Then we write the header, which corresponds to the message type, which I also defined earlier in the protocol. Once we've written the beginning of our message, we can then write the data. So for the note press message, we just write the note number, which is a single byte. And then we call this end message, which just delays a little bit because we want to make sure that the backend has received the message and has time to process it before we send the next message. So on the other side of our code base, inside of the backend, we have the receive frontend file here. And what's happening here is a little bit more complicated because it has to then interpret the bytes which are being sent from the front end. So once again, we're using the Arduino serial object, which in this case we're using serial 6. And in this file we have this method here which we're going to call continuously. And what this does is essentially tries to read from the UART and asks it, hey, do you have any new information for us? So if it doesn't, it's just going to send us a -1 and we're going to skip this whole block here. But if we do get a byte, we then have to look at what the byte is. So in order to keep track of where we are in our message, we have this write head, and then we have this buffer which we're writing the message to. So by default, the write head is going to be set to -1, and that essentially means that there's no message in the buffer and we are listening for the start of the message. So in that case, we're going to check if the write head is detached, which means that it's -1. And only if we receive the message begin do we then start listening to the message by setting the write head to 0. Otherwise, if we get a different byte here and the write head is still detached, we're just going to ignore that byte and we're going to keep listening until we one day get the message begin. So once we have the write head set to 0, that means we're going to start reading our message and writing it into the buffer. So now any bytes that we receive after this are going to go into the message buffer, and then we increment the message buffer write head. Once the message buffer write head reaches the length of the message, we then know that the message is over. And we know the length of the message based on the header. So here we have a method here which is going to get the current message header, and then as defined by the protocol, each header corresponds to a certain message size. So once we've reached the end of the message in our buffer, we can then handle the message because we have the entire thing. So this function here handles the messages, and that takes in the buffer that we've just written to. And depending on the type of message, it will dispatch it to different parts of the program. So for example, here it's going to begin voice when it receives a note press, release the voice when it receives a note release, and so on. So now we can try out our keyboard and we can actually play notes with the buttons on the keyboard. So real quick, I want to talk about the design of the keyboard and how I'm laying out the notes here. So initially my plan was to just have a semitone scale on each row, so going like this would be playing semitones, and then I'd have a second row up here. But I thought about it a little bit more and I've realized that maybe there's a better way of laying the keyboard out here. So what I've realized is that the keyboard is made up of these 4 keys in each column, and what's nice about that is that that fits into an octave neatly, because you have 12 notes in an octave, so 4 divides it perfectly into 3. So initially my plan was that going like this would be ascending semitones, but then I realized there'd be a problem where if you're trying to play notes down here and you wanted to play a chord, you'd have to do a weird thing where you stretch your fingers like this. So instead what I've done is I've grouped them into columns of 3. So you can see that's 1 octave there. So now we have 4 columns is 1 octave. And the reason I've done that is so that now the bottom row is going to duplicate the top row. And what's good about that is that it means that playing chords becomes much more easy once we reach the bottom row. So for example, a major chord with this arrangement looks like this. And what's nice about this arrangement is that no matter where on the keyboard, these are all major chords. But also because the bottom row is identical to the top row, it means that when I play a chord near the bottom, I can use the bottom here instead of needing to wrap my hand around and do something awkward. It's more intuitive, and it means that essentially the major chord is always going to be the same no matter where I am on the keyboard. Another thing you might want to know is like, how would you play a major scale? And that kind of looks like this. We can play chords in the left hand, and then we can play a melody. So I need to practice on this. It's quite different from a normal piano. It's quite difficult to get used to. Another thing that's kind of fun is trying to type out words and seeing what it sounds like. So let's type something like hello world. How are you doing? Anyway, so that's how we're laying out the keyboard notes, and it also shows that the UART thing that we've done has worked successfully, and now the two halves are communicating with each other. So let's talk about the screen that I've chosen. So I've gone with this Adafruit screen, and Adafruit are a company that make breakout boards, and a breakout board is essentially a combination of various components which can be handily wrapped up into a package and treated as one bigger component. So in this case they've packaged the screen, and they've also packaged in a touch screen, and then also along with those two things they've packaged in a microcontroller which can control the touchscreen and the screen itself. So this is how the thing is going to be wired. We have 8 wires, which are the data bus, and that's going to be able to send data to the microcontroller, but also send data to the screen, so it goes both ways. And then we have these 4 pins here, which are used to control the screen. So I'm just going to show you an example of how you would send a command from the microcontroller over to the screen. So here are the pins. We've got the 4 control pins. And then below here I've just written those 8 wires as a single byte in hexadecimal. And when it's green, that means the pin is high, and when it's white, the pin is low. So by default all the pins remain high, and then to turn them on you kind of paradoxically turn them low. So in order to send a command, we need to send the command pin to low, then we need to set the chip select pin to low, which means that the screen is going to start listening to what we're going to say. And then lastly, we can write our command to the data bus here, and then we need to toggle the right pin on and off. And similarly, to then write data, we set the command pin to high, and then we can write data. So what this is going to do is going to say execute command 2A with data 04. So then in order to draw a pixel on the screen, you first need to define the area to which you're drawing pixels. So you first need to specify the columns which you're going to start and end at. These are encoded as 2 16-bit numbers, and each 16-bit number is 2 8-bit numbers. So all in all, you need to write 4 separate numbers after writing the command 2A. Similarly, you can use the command 2B to then define the top and bottom of the area that we're going to draw to. And then lastly, you send the command 2C, and then stream bytes from the data bus which represent the pixels, and each pixel is 16-bit, which means it's another 2 bytes. And so after that you can just draw all the pixels in the area that you've defined. So thankfully for us, the Adafruit company have supplied a handy library with their breakout board, and that's capable of drawing lines, drawing rectangles, and rendering text. So let's look at this Adafruit screen library. So the way you define it is just to define the number of pins that you're using, and then you can instantiate this object here. And then from there you need to initialize the object. And here I'm just running the basic screen test which came with the library. So this just does stuff like fill the screen with various colors, draws a bunch of lines, text, this sort of thing. And this is just done to profile the screen and make sure everything works. So here we have our screen set up. I've already plugged everything in, and I'm using these temporary wires because I'm not entirely sure how I'm going to fit it in neatly with the rest of the system, but for now we're just kind of wiring everything manually. So here we have our 8 data lines here, and then over here we have our control pins, as you can see marked here. And then lastly I've attached the wire here so that it's flipped on with the upper microcontroller. And that's just so that I can turn this screen on and off independently from the lower microcontroller, which is the one controlling it. So now let's run our screen test. So you can see here that it's drawing all the different shapes, drawing various lines as well. So there is a problem with this library. If you saw the graphics demo just now, you may have noticed that it is a little bit slow, and in fact that's the thing running at full speed. So we've measured here the amount of times it takes to do all of these tests, and some of them are in the range of 1,000 milliseconds, which is way too high if you think about it. We want the synthesizer to be responsive, and if it's spending a whole second trying to draw something, that's going to be a problem. So in a future video I'm going to talk about how to optimize this library, but for now I think I'm going to leave it here. So in this episode we did manage to finish most of the hardware side of the synthesizer, and now it's going to start the long road to writing all of the software for this thing. So next time we're going to explore musical synthesis basics. Previously we did just audio basics, which is how to get audio out of a synthesizer, but now we're going to actually talk about how to make that audio sound good, how to generate waveforms, filters, LFOs, all that good stuff. So I hope to see you then, and thanks for watching.